Hello. So this session is about mountain glaciers, and we have two talks. One is about glacier projections and Paris limits, and then we have a second talk by Miriam Jackson about changes in mountain glaciers in the high mountain Asia. There are more than 270,000 glaciers outside the ice sheets. So there are 270,000 glaciers outside the ice sheets. And these glaciers are losing mass and retreating worldwide. So here an example here from Argentina, another example here from Alaska. And what we see is now there's massive, very, very quick changes just in the last years. Here's an example in Switzerland. This is just within 8 years, massive changes. So we really see an acceleration in the mass loss. Or here, another example. So we see actually smaller glaciers are disappearing worldwide, and we have massive, for instance, massive mass losses here in the European Alps. Within just 2 years, in 2022 and 2023, 10% of the entire glacier volume in Switzerland disappeared. And 2024 seems also to be a record year. There's record melt in Svalbard and other regions of the world. When we look on a global scale, what you see here is the thinning rates of all glaciers in the world outside the ice sheets. So each colored dot is the area where there's glaciers. Blue is thickening of the glaciers during this period here, this 20-year period. Light yellow is no changes, and dark red is more than a meter of thinning. And you see, on average, globally average, we have a thinning rate of about 50 to 60 centimeters per year during this period. So every year, half a meter or more thinning on average over all glaciers in the world. But regionally, you see there's huge differences. In many areas, there are sort of sub-regions where we have thinning rates of a meter or more. And why does it matter? It matters for it impacts natural and human systems. It impacts sea level rise, freshwater resources, landslides, hazards, glacier outbursts, floods, water quality, of landscape changes. So I just want to go through a little bit the changes, also what happens in the future. So how will the glaciers change in the future? Here you see projections of Alch Glacier in Switzerland, the biggest glacier in the European Alps, for a low emission scenario and a high emission scenario. And what you see until the middle of the century, there's not much difference, but then it's a huge difference if you have a high emission scenario or a low emission scenario. The high emission scenario, essentially the glacier is gone. When we look on a global scale, here you see the regional glacier projections between 2015 to 2100. And one means 100% of the glacier mass, and then we see how much mass is remaining relative to 2015. And what we see here on the global scale, we have mass losses of about 20 to 40%, which is corresponds to a sea level equivalent of about 8 millimeters to 17 millimeters. And what we see is large regional differences. It's here shown for two emission scenarios, a low emission and a high emission scenario. In regions where there's a lot of ice, like in Alaska or Arctic Canada or Russian Arctic, the mass losses are in the order of 10, 20, 30%. But in regions with little ice, or like Scandinavia or Caucasus, tropics, European Alps, there's massive changes by the end of the century, mass losses in the order of 80, 90 to almost 100%. So almost complete deglaciation in these regions that have very little ice under a higher emission scenario. So we calculated here, we are converted our simulations as a function of temperature, global mean temperature increase above pre-industrial. So the question is here, how much glacier mass would remain in 2100 for the Paris target and other temperature limits? So here, for a temperature increase of 1.5 degree, the lower limit of the Paris target, what you see here is the mass that is remaining at the end of the century. And blue is almost dark blue, almost 100% is remaining. Dark red is almost nothing is remaining. And the black circles show that no ice is remaining in these regions. So even for 1.5 degree, you see massive glacier changes. And here, especially in the low latitudes and in mid latitudes, we see almost complete deglaciation, even for 1.5 degrees in many of these regions. Here you see for plus 2 degrees. You see more red, you see more of the black circles. Plus 3 degrees, plus 4 degrees. And yeah, just go back here. Plus 4 degrees is almost complete deglaciation in almost all regions, except for the very high Arctic or here close on the Antarctic islands, where there's still quite some ice left. What you see here is the mass losses expressed as a function of global mean temperature increase above pre-industrial. And what you see here is almost a linear relationship between mass loss and area loss as a function of global mean temperature increase. So for instance, for a 2 degree temperature increase, we have 45% mass loss and 30% area loss. So really, each degree makes a huge difference. Each increment of a degree temperature increase matters. We also calculated that even for just a 1.5 scenario, half of the glaciers in the world, more than 100,000 glaciers, are projected to disappear by 2100. But most of these that are projected to disappear are also very small, less than 1 square kilometer. Here you see the same type of figure. We see how much mass is remaining as a function of global mean temperature increase, but here shown for all the 19 regions. We see in regions where there's a lot of ice, there's almost a linear relationship, although the the spread varies between the regions. In regions with little ice, here again, like Scandinavia, North Asia, New Zealand, low latitudes, Caucasus, we see it doesn't really make much difference anymore if it's plus 3 degrees, plus 4, or plus 5. And that is because there is essentially complete deglaciation for plus 3 degrees or beyond. But it is very high, these regions here, it's very, very sensitive for temperature increases between 1.5 and 3 degrees. So it really makes a huge difference how much ice is left, if it's 1.5 or 2 degrees or 2.5 degrees. And though these regions don't really matter for sea level rise, these decreases in glacier mass have major implications for water resources. So then we did some calculations here. What if the climate can be stabilized? So, and now we are not looking at trends in climate scenarios and until 2100, we force the models with different temperature scenarios, 1.5, 2 degrees, 2.5, 3 degrees, and so on, and keep that climate constant. So the glaciers, they retreat. It takes some time. There's a delay. We want to know, like, at what level will they stabilize? And also, how long does it take? So here are the simulations. We looked at 80 climate scenarios, varying in the temperature increase from almost 0 to almost 7 degrees. Each of these lines is a scenario, and here dashed line shows it for a few selected temperature increases. So what you see, there's initially a rapid decline in glacier mass, And then at some point, the mass stabilizes, the glaciers reach a new equilibrium and don't change anymore. So and then we wait until they reach a steady state. We calculate for thousands of years until the glacier mass remains constant. And then we calculate what is the committed mass loss, the mass loss that's going to happen even if climate just change further. So it's the difference between the present day mass that we have and the mass at when the glaciers have stabilized. And this is here the result for 1.2 degrees, which is essentially present day. This is what we take for present day. So if we just leave the current climate constant, we don't change it at all, what you see here, the blue circles for all the 19 regions, how much mass is lost. So if the circle is completely blue, 100% is lost. And what we see on a global scale, almost 40% of mass is lost, even without any further climate change, if we just leave the current climate constant. So this is really the committed mass loss, not yet realized, even if we leave the climate constant. But we have huge regional differences. Here in South Asia West, it's only 5% lost. So most of the mass is still there. But in Arctic Canada South, we have 80% of the mass lost, even if we keep the current climate constant and have no further increase in temperature. The same here for 1.5 degrees. So you see now here the green lines popping up. So in some regions, a lot more mass loss, just the difference between 1.2 degrees and 1.5 degrees. Globally, almost half of the mass loss for 1.5 Paris target, Paris Agreement target. For 2 degrees, the higher temperature increase, the target for the Paris, we have 63% of mass loss eventually for the 2.0 global mean temperature increase. And you see also you're very sensitive in one region, a lot more mass is lost here just by jumping from 1.5 degrees to 2 degrees plus. Here for 3 degrees, a lot more. This is another way just to present the data. So I just walk you through. You have all the 19 regions and the globe. You have the mass losses here for 1.2, 1.5, 2, and so on. 2.7 is shown because this is the trajectory we are on right now. And then colored here by how much mass loss you have. And for 1.2, we see this huge difference between the regions from like 5% to 85%. But for like 2 or 2.7 or 3 degrees, the differences are no longer very big. So all these regions for plus 3 degrees, so almost the trajectory we are on, will lose at least 60 to 80% of their, or even 100% of their mass. So the regional differences, they level out. Huge regional differences for 1.2 degrees, but then for higher temperature levels, it's almost complete deglaciation in many regions. So here you see all the data, all the simulations, the mass relative to 2020 as a function of warming level. So how much mass is remaining? And as expected here, the higher the temperature level, the less mass is remaining. And it's almost linear here in this area between 1.5 and 3 degrees. Then it levels out, and that is simply because in many regions the glaciers are gone. So for 1.2 degrees, again, we have 39%. For 1.5 to 2, the Paris Agreement, 47 to 64% mass loss. The current trajectory, 76% mass loss by the end of, once the glaciers have stabilized. So we also addressed the question then, how long does it take for the glaciers to find a new equilibrium? So as said, we run the models for thousands of years, and it takes a couple of decades, it takes several decades to, in many cases, actually many centuries until the glaciers stabilize. So here again, back to our simulations, very rapid decline, very rapid mass loss in the first decades or 100 or 200 years, and then it levels out. But it's just to show here, this is 2,100. So most of the previous projections stopped there. What I showed in the beginning was the mass losses until 2,100. But look here at plus 2 degrees. For plus 2 degrees, the yellow line, there's still 70% of mass is left in 2,100. But once the glaciers have stabilized, it's only 33 or 35%. So we need to look at longer timescales. A lot of the mass loss is not done by the end of the century. Even if the climate doesn't change anymore, the glaciers continue to lose mass. So there's a considerable additional mass losses beyond 2,100. One really needs to look at bigger timescales. So I just want to close off here with some key messages. Here, almost 40% committed global mass loss under present-day climate conditions. So no further climate change, just present-day climate conditions. Eventually, not by 2100, but over centuries, we lose 40% of all glaciers. And for 2 degrees, it's 64, and the higher the temperature level, the more we lose. So even the key message here is, even if the climate stabilizes at a constant temperature, glaciers will continue to lose mass for decades and even centuries. However, the total mass loss can significantly be reduced through implementation of stringent climate policies. So really, every increase of temperature matters. So there's still some hope. It's really every increase matters. Even though a lot will be lost, it's done, it's committed, but we have it really in our hands how much will be lost eventually. Thank you. Any questions? Otherwise, we move on to Miriam. So Miriam, please.
Thank you very much, Regina. That was a fascinating but also depressing overview of what's happened so far and what's probably going to happen. So that was talking about glaciers globally, and the glaciers are reacting differently in different parts of the world. And certainly in the European Alps, in the Caucasus, tropical glaciers, they're already melting very fast, and they're going to melt very fast. In other parts of the world, for example, high mountain Asia, especially the Hindu Kush Himalaya, the glaciers aren't melting as fast. They're going at a slightly slower rate. However, there's one big difference. In high mountain Asia, there's hundreds of millions of people who are dependent on water from glacier and snow runoff. And there's also billions of people who live in river basins that are fed by glacier and snow runoff. So this means that although the cryosphere isn't reacting as fast, the implications are much, much bigger. So I'm presently the Eurasia and Nordic Director at ICCI. I'm also working as a glaciologist for the Norwegian government. But until very recently, I was working for ICIMOD and based in Kathmandu, Nepal. So I was working in the Hindu Kush Himalaya region and a little bit in Central Asia. So I'd like to bring you, I'm going to show one or two figures from a report we released recently called HighWise, and this is looking at the changes in the cryosphere and projected changes, and also how it's affecting water resources, hazards, ecosystems, and livelihoods. And this is similar to what McGee already showed. It's basically just showing the different regions that are used in the Randolph Glacier inventory. If you look on the right-hand side, you can see the regions 13, 14, and 15. So they're the regions I'm going to be talking about. And this is looking at what's happened over the past few decades in the different parts of regions 13, 14, and 15. And what this is showing the health of the glacier. So if the glacier is getting bigger, you see blue. If the glacier is getting smaller, you see red. So this I know it's quite complex, a lot of information, but they're the main things we need to know. So this is where we have audience participation. What do we see on this graph? Do we see mainly red or blue? We see a lot of red. Good, we've got a shy audience today. And we're also looking, and especially if you look at Eastern Himalaya, if you look at, at Sikkim, at Bhutan, the glaciers are really melting fast there. We're also looking at 3 different periods. So we've got 1975 to 1999, 2000 to 2009, and then 2010 to 2019. Regina actually showed results globally for 2000 to 2019, but we split them up. And so you can see going from left to right, the 3 different periods. Again, what do you see? Are things getting better or getting worse? Thank you. It's pretty clear that things are getting worse. There was a 66% increase in glacier melt in the last decade compared with the previous decade. So although things are happening more slowly in high mountain Asia and in the HKH, it's still speeding up. You also see a little bit of blue here. We used to call this Karakoram anomaly. And recent results seem to show that that basically doesn't exist anymore. Glaciers are pretty much in mass balance or even losing mass. So what does that actually look like, the changes on the ground? This is Yala Glacier. This is a glacier in Nepal. It's quite small. It's been used for a lot of glacier training. A lot of glaciologists in Asia and in Europe, other places have been on this glacier and learned how to do glacier measurements. We haven't got continuous measurements going back to 1982, but we have several years and also continuous going back to about 2010. And it's really changing. I don't even know if it's a glacier anymore. A glacier deforms under its own weight. And this has pretty much gone from a glacier to a big ice cube. We've even added it to the glacier casualty list. This is a list of glaciers that have either recently disappeared or are going to disappear very soon. This is another glacier in Nepal, Rikasamba. Again, it hasn't been measured continuously all this time, but it's been measured at different periods. You can see how it looks at different times. And again, you can see big changes. This is the graphs that we were showing. This is what it actually looks like on the ground. And when we talk about increase in temperature, increase in carbon dioxide, it doesn't really mean very much. It's not something that you really feel or sense. When you actually see a glacier and what happens when the carbon dioxide, greenhouse gases increase, when the temperature increases, this is what it looks like. You can see that something's really happening here. A few figures also that I've picked up over the last few days. Tajikistan previously said they had 14,000 glaciers. Now the number's gone down 1,000 already. This is a huge decrease. Pakistan actually has the largest number of glaciers outside the polar regions. And I was in northern Pakistan just a few weeks ago in September, and it surprised me because it's very dry there. It's almost like a desert, but they get a lot of the runoff from glacier melt and snow melt. And also a lot of people there work in agriculture and they use the water for irrigation as well. If that water is decreasing, then they really have problems. And they also spend a lot of their income on food. So if the food prices increase, this is going to have a huge effect. There's also millions of people at risk of these glacial lake outburst floods as well. As the glaciers get smaller, glacial lakes are formed and they get bigger. We also have very few measurements in the HKH. We have a lot of measurements in Europe, in Scandinavia, North America. When you're simulating what's going to happen with the glaciers, it's really useful to have these measurements. If you don't have the measurements on the ground, it makes it a little bit harder. You don't know as much. And certainly in the Hindu Kush, Himalaya and Central Asia, there's been much fewer measurements than there has been in some parts of the world. So these are some of the measurement series in Nepal. Also, for example, AX01 is very, very small. Again, it's not really a representative glacier. And why is that? There's a few different reasons. One reason is just logistics. When I work in Norway, we can use helicopters, we can use snowmobiles, perhaps we can ski for a few hours or many hours because I'm a slow skier. It's easy. We can also look at the weather forecast. We travel and do field work when the weather forecast is good. And the Himalayas is very different. It takes several days just to walk up to where the glaciers are. It might take you a whole day just to drive 100 or so kilometers just to get to the point where you start walking. So this is much harder. You can't really plan to go when the weather's good. You have to plan in advance because you're away a long time. you can end up having terrible weather. That's certainly happened to us a few times. So it makes it much harder. In Central Asia, they had quite good measurements in the 70s and 80s and early 90s. And then there was political change. We had this big gap in the middle. Scientists have tried to go back and sort of fill in the gaps, but we don't have the information on the ground. There was no measurements for several years. So again, it makes it much harder to know exactly how the glaciers are behaving and to calibrate your models. Another thing that happens in high mountain Asia, well, anywhere when the glaciers change, is you have a change in hazards. And as mentioned, one of these hazards is the glacial lake outburst floods. And when I was in Norway, we had quite a few of these. We usually had several a year, and we'd have a lake that would flood, and then the water might go into a hydropower reservoir, or it might actually just flow straight into the sea. In high mountain Asia, when it happens, often it affects many people. So it's not just the hazards that's the problem, it's also the exposure, how many people are going to be affected. Is it a small community, perhaps some tourist cabins? Or is it several settlements, hundreds or thousands of people that live downstream? So we don't just look at the hazard, we also have to look at the exposure, who's exposed, and the vulnerability. And there's been a figure mentioned actually a few times this week that there's 200 glaciers that are potentially dangerous in the Hindu Kush Himalaya. I need to qualify that statement. There's at least 200 glaciers that are potentially dangerous. There's more that are dangerous. We just haven't identified them. In August this year, there was a small outburst flood from Tammy. You might remember it. And it wasn't on our list. We hadn't identified it. Why not? It was so small. So we thought it wasn't important. Fortunately, when it happened, nobody was killed. But there was a lot of damage. Many buildings, I think, to one health post and a couple of schools were damaged. People's buildings, agricultural land were damaged. And this was a very small lake. But the people here are so exposed and so vulnerable that it does make it much more difficult. There's also several challenges in draining the lakes. This has been done both in Europe, it has been done in the HKH. They tried doing this in Bhutan, but they had to take several hundred people up to 5,000 meters over 4 years to do this. So it's a bit more challenging than when we did it in Norway and we just used a bulldozer. This gives you some idea of how many there have been. This is for all of high mountain Asia. Again, these numbers aren't absolutely correct. These numbers are minimums. There could have been other floods in the past we didn't know about. We didn't identify them as glacial lake outburst floods. So they're not added to our list. But we do know that these floods have already killed thousands of people, have caused millions of dollars worth of damage, and that also the number of lakes are increasing, the size of the lakes is increasing, and these are going to become more common. If you want to use this, you can go to this thing. This is one interesting example we had. A couple of things to note here. This came from a lake called, I can't pronounce it, Gongwatangsha. I don't know if anybody knows where that is. This is a quiz part of the talk. Gongwatangsha. This is, fun? Whereabouts is this lake? No, the lake, Gongwatangsha. This is in China. Where's Bodhikoshi? This is in Nepal. So these hazards are transboundary. How do you drain a lake when it's in a different country? How do you put in early warning systems close to the lake when it's in a different country? And this is one of the challenges in high mountain Asia, that these hazards are transboundary, often between countries that aren't always working very effectively together. So this is what we're looking at. If we keep the 1.5 to 2 degrees, we're going to lose a lot of ice in the Hindu Kush Himalaya. If we have higher temperature increases, we're going to use a huge amount of ice, and this is going to really have a very big impact on the livelihoods in many countries in Central Asia and in the Hindu Kush Himalaya. Thank you very much. Any questions? Yes.
Reversing back.
There's several ways to reverse it back. One way is to reduce greenhouse gases. If we do that, we reverse it globally, or we slow it down. Well, it's already some locked in, yes. I mean, there's one thing, we're already locked in, even if we, stop all emissions of greenhouse gases. Another important thing is to slow things down. People are flexible. They can adapt to a lot of different things. But if you can adapt more slowly, it makes it a lot easier. If the changes are happening very fast, it makes it a lot harder to adapt. There's other geoengineering solutions, but as Regina said, there's hundreds of thousands of glaciers in the world. Is there a simple solution for hundreds of thousands of glaciers? No, except reduce greenhouse gases. This is also a problem. So a lot of the times in high mountain Asia, we talk about, cascading risks and multiple hazards. And there was an earthquake in Nepal in 2015. And one of the things that happened is it caused an ice avalanche from the ice above Langchang village. And then, this mixed up with the rocks. We had a lot of ice and rock coming down, and this had a terrible effect, that over 100 people were killed, whole families wiped out, most of the village was just obliterated. So, when you combine several hazards together, the Hindu-Kush Himalaya has a lot of seismicity, is high seismicity. This makes the problems even worse, the challenges even greater. So the question is how the teams are studying the glaciers and if they're collecting ice cores. So there's a lot of different teams. I showed a couple of glaciers where ICIMOD's working, but ICIMOD's actually a group of 8 different countries. So China is also a part of ICIMOD, and of course they're doing their own work and they're collecting ice cores. We do have some people taking shallow ice cores, but generally the goal is really to look at the mass balance and to, do the normal stake measurements and just see if the glacier is getting bigger or smaller. Usually it's getting smaller. So there has been some coring done, but it is very challenging doing it in this area.
The average recently we had a blog in what we realized in today's we are focusing more on the best in projects aside. What's the one lesson that you had recently in office? The team actually not actually schools until last year.
Yeah.
We are very active.
Yeah.
So what are the 15 users that the guys working on this working because we have to focus more on like a bigger deals and we have to have
Okay. Yeah. So good question. It's about the glacial lakes and especially the event in August this year. And I did mention it. I think you came a little bit through, so you might have missed it. And this was important because there's been identified 200 lakes that we think are potentially dangerous, and they've been categorized. And the one that at Tamel wasn't on the list, and that's because it was so small. So it's there's a lot of lakes that are potentially dangerous, but they're not as dangerous as some of the other ones. And we don't have the capacity, to keep an eye on all these lakes. But people in downstream communities, who live downstream of the cryosphere, have to be aware the cryosphere is changing. And, even if there isn't a lake, the lakes form quite quickly. So, and often these areas, people don't go up there very much. So, the lakes could quickly form and then burst out and cause a lot of damage. The one in August, fortunately there were no fatalities, but it caused a lot of damage. And this is something that could happen anywhere else. There's also one in Sikkim in October last year. That was also a very interesting one because it had been studied. There'd been previous attempts to lower the lake level, but it was, what's the hurry? Nothing had happened yet. They started putting an early warning system, didn't quite get finished, and then suddenly the lake, bursts. Over 100 people are killed. Hydropower plants wiped out. Bridges, roads. Getting around Sikkim was really challenging, and that for me is very typical of what we're facing here because people knew about this problem. They knew that there was a problem at South Lonak Lake, one or two others in Sikkim, and they were going to do something, but they did things too slowly. In the end, the amount of money that was, involved in economic losses and, of course, the loss of life is much, much greater than if they'd done some mitigation efforts before the event happened. So we really have to make people aware of this.
As places melt, so the top goes up and then it goes down.
Right. Yeah.
Is the thing true for glacial lake up? You get more frequent glacial lake up sponge before then the glaciers die and then they're getting.
I mean, certainly when the water from the glacier is increasing, then it's going to be more likely that you get the lake forming. And also things are happening very quickly. So I know some people have been looking at that. I think it's a little. I couldn't really give you a good answer, but I think certainly as things are changing faster and there's more water coming from the glacier, you're going to get more lakes being formed and being formed faster, and more chance of them, bursting out in a flood just because things are changing so fast. And also the other things about gloss is often there's other factors involved. A lot where the glacial lakes are, the ground is frozen, there's permafrost. And as the permafrost thaws, it could fall into the lake and trigger a glow. This is probably what happened in South Lonak in Sikkim. Or you could get an avalanche going into a lake. This also triggered a smaller one in Nepal earlier this year. Yes, we're definitely looking at the implications of water supply. And Regina mentioned peak water, and Robbie did as well, that as the glacier melts, the water increases and then it decreases. In some parts of the world, like in Europe, where past peak water, the water is decreasing. In the HKH, it's generally increasing still. Of course, it varies from basin to basin, but it's increasing. And then about 2050, say, then it'll start decreasing. And this is quite a complex message to get across. Because, you can say to people, there's going to be more water or there's going to be less water. You have to try and tell people there's going to be both, and if they're, doing agriculture, depending on a certain amount of water, they have to be aware of that. If they're living very close to the river, they have to be aware it's going to be more water. But then how much do you want to spend in developing? It's going to be less water. You also don't want to be having, developing agricultural land that needs a lot of water. And also for hydropower development. It takes a long time to plan hydropower. It takes a long time to build. For it to be profitable, you're looking several decades ahead. So you have to make sure that, your hydropower is going to be running long enough that you're actually going to make some money on it. Okay, good. Thank you very much. Good.